Let's pretend that we're going to take a survey and someone polled our community and they asked 300 people about the new Granger High School. They discovered that 84% of people are excited for our new school building. Another poll taken a few weeks later said that 80% of people are excited for the new building. So the question we might ask is, does that mean one of the polls, one of the surveys, remember, okay, we're just talking survey here, is one of the surveys wrong? Or really, in a matter of just a couple weeks, did people change their opinion? Hopefully you're thinking in your mind, well, maybe not. Maybe there's nothing wrong. We expect to see variation in sampling. We took 2 different surveys, and we got 2 slightly different results. Hopefully that's not surprising. We expect to see little differences just because we're sampling. Right? The 84%, that was a different group of people than the 80%. And again, just by chance, right? Just by chance, we're going to get little differences. So you saw, I said, but how different, right? We should see little differences due to chance. Right? One day I ask people, and based just on the random 300 people, maybe one day I get 84%, maybe the next day I get 83%. So the question is seeing 80%, is that weird different? Is it still believable? So that's what we're going to be checking out. Okay. So just to help us understand what we're doing, we're going to be talking about what's called a sampling distribution. So kind of put those 2 words together, distribution. Hopefully at this point you can kind of picture. A distribution just means how the data is spread out, and it's a sampling distribution. What would sampling over and over look like? So imagine if we took a sample after sample after sample. So I'm just going to make a little number line here. I'll put 84%, 85, 86, 87, 88, maybe that's 88%. 83, 82, 81, maybe this is 80. The idea is I go out, I ask 300 people, and I get some result. I don't know, maybe I get 84%. And then let's just pretend that I went out and I chose another 300 people. Now it's random, so I might get some of the same people, I might get totally different people, but I'm going to get a different result. There's no way I'm going to get exactly 84% again. So I don't know, maybe this time I get 86%. Weird, right? And then I go out and I do it again. I collect another 300 people and I ask them the same question. Maybe this time I get 83%. And I do it again. And I do it again. Maybe I get 84 again. And I do it again. And I do it again. And I'm getting, of course I could get things in between, like 84.5%. So I'm just doing this over and over. And sometimes I get the same answer and sometimes I don't. But the idea is that's what a sampling distribution is. What will this graph look like when I'm all done? Now, in real life, we never ever take sample after sample after sample. We don't do that. We go out, we gather one sample, we call it good. But I just want you to imagine, what if? What if? Well, something kind of cool happens. If we do this long enough, we actually end up with a normal model. Amazing. Really cool that it happens. So let's talk about that. We end up with a normal model. It's going to be centered. Remember, this is the mean. It's going to be centered at P. P represents the true proportion of whatever it is we're asking about. So in this case, it would be of new building supporters. All right, so our normal model will be centered to that proportion. And then this is our formula for how we figure out the standard deviation. We take P times Q, remember from your probability days. Q is just 1 minus P. And we divide that by N, and we take the square root. So suppose it's true. Suppose I have a magic crystal ball, and I know that, out there in West Valley City, 84% of people are just really excited about our new building. So what would the model, how could I represent all the possible samples? Well, it's going to look like a normal model. it's going to be centered at p, the true proportion. Now, I like to use decimals instead of percentages. And then I could actually figure out 1, 2, and 3 standard deviations going up and down using this formula, this PQ over N square root. So I'll go ahead and do that. P is 0.84. That means Q is going to be 0.16. And I'm going to divide it by N. Remember, I said we were asking 300 people. And then I'm going to take the square root of that. Just a quick suggestion. If you're going to do this in your calculator, I would actually do all the stuff inside. And then I would just square root my answer. That's a kind of maybe easier way to make sure you don't make any mistakes with your parentheses. All right, so that was approximately 0.021. So using that information, this is back to Chapter 6 ideas, I can just fill in my normal model. I have to write just a little smaller there to get it all in. Okay, so what does this tell us? Well, this tells us that if we were to go out and take lots and lots of samples of 300 people, if I got this sample that was, the 84%, I got my other one that was 80%, and I just did this over and over and over and over and over and over, lots and lots and lots and lots. Remember, going up to and down to, that means 95% of the time, I'm going to get answers. When I ask people, what percent, I ask people, do you support the Granger High School building? I'm going to end up 95% of the time getting between 79.8% saying yes and 88.2% saying yes. Wow, 95% of my samples would have proportions in this range. All right, so the question says, what do you think about that survey that got 80%? Maybe think, is it weird? Well, hopefully you're saying in your mind, no, like 80% is right here. That's within 95%. So this is not weird. 80% was just chance. Now, if one day I'd gotten a survey that said, 73% of people support the new building, now I'm a little suspicious, right? Why on earth would I be getting 73%? If it's really 84% of people. Okay. So this is just giving us an idea about what to expect when we sample. All right, so can we always use a normal model? We get really excited. The short answer is no, we cannot always use a normal model. So in order to decide whether or not you should, you need to check your conditions. We've seen these before, this idea of having conditions. So the 3 conditions for you to check. Number 1, data should come from a random sample. Very important. Number 2, your sample needs to be less, this is a less than sign, less than 10% of the total population. For example, I asked 300 people this question about Granger High School. So I have to ask myself, well, 10%, that would mean there needs to be like 3,000 people living in West Valley in order for this to be less than 10%. That's probably true. I imagine there are lots more than 3,000 people living in West Valley City. So my sample needs to be smaller than 10% of the entire population. All right, and then number 3, I calculate NP, NNP. Remember, N is your sample size, and P, that's your proportion, your percentage. That number should come out to be greater than or equal to 10. And I do the same thing with Q. Remember, sample size is N, and Q, remember, is just 1 minus P. All right, so if those 3 things are satisfied, we can use the normal model, as I showed in the example. All right, so let's do just one more example so you can see this kind of in action. Of all the cars on the interstate, so thinking freeway, 80% exceed the speed limit. I just have a magic crystal ball, and I know for a fact 80% of cars speed on the freeway. Just magic knowledge I have. So the question is, what proportion of speeders might we see among the next 50 cars? I'm not going to see exactly the perfect 80%. That's because I'm taking a sample. All right, so before I get excited and draw a normal model, I am going to check those conditions. Do I have a random sample? As a matter of fact, no, I don't. I'm just taking the next 50 cars that come. That's not random, but I do think it is what I'm going to call representative. Those next 50 cars represent any 50 cars I could choose. There's no reason to think the next 50 cars are special or different in some way. All right, 50, is that less than 10% of my population? That would be cars on the freeway. Yeah, I'm pretty sure in order for this to be 10%, there'd have to be 500 cars on the freeway. Pretty sure it's higher than that, so we're okay. And then I'm going to calculate this NP and NQ. Well, let's see, N is my sample size. I'm checking 50 cars. P represents the true proportion, that's speed. I know that 80% speed. So that gives me 40. That number is greater than or equal to 10. So we're good there. One more, I have to check N times Q. Remember, N is my sample size. If P was 0.8, then Q will be 0.2. So that comes out to be 10. Ooh, 10 is greater than or equal to 10. So we're okay there. Okay, so since our conditions are met, we can go ahead and draw the normal model. So I'll do that. I'll try again to do that right here. So remember, this normal model is centered at P with the standard deviation PQ over N square root. That means P is going to be centered at the true proportion of speeders. That was that 80%. And then to calculate this, I'm going to need the square root of P times Q over N, checking 50 speeders, and I will square root that. So that comes out to be approximately, when I put that in my calculator, 0.057. So I can just quickly create this normal model. Again, you'll notice I'm doing up and down 3 standard deviations. All right, so what proportions might we see? Well, 95% of our samples, 95% of my samples would be between, or I should say would, perhaps I should say would give proportions between 68.6% and 91.4%. So notice there's a lot of variation in there. It's true that 80% of speeders, 80% of cars speed on the freeway, but I could see as low as 68% or as high as like 91%. Without that being unusual in any way. Just remember, within that 95%, that's not unusual. So suppose a police officer says one day he saw only 67% of speeders during his shift. So he also saw 50 cars. If you were his boss, would you believe him? Well, notice where 67 is. Right outside that 95%. So is it likely to see 67% speeders? No. This is not likely. But is it crazy, weird, far away, unbelievable? Maybe not. Maybe not. So would you believe him? That might be up to you. Again, 67% is not likely, but it's also not extremely strange. It's not past 3 standard deviations. So I might think, what do I know about that officer? Has he lied before? So what? Why are we bothering to do this? Well, Chapter 18 is going to be the foundation for everything else we're going to be working on for actually the rest of the year. So we are building some important foundational knowledge here.